Hi, it's Dr. Fox here. This is the second lesson in a series of lessons from thermal physics, part of the AQA physics course. This is now moving into the gases area. We dealt with solids and liquids and gases and state changes before with simple specific heat capacity. I always want to say simple harmonic motion. Specific heat capacity and specific latent heat. This is all to do with gases now, and more accurately ideal gases. So we're getting rid of those pesky things called intermolecular forces and size and all those sensible things which are doing with physics. But actually what's really good about this historically is that it works. It works really well. All models of matter are a model, and they're as close as we can get. But if it describes what we see, then let's go with that theory. It works. Okay, so just to run through this, we're going to look at pressure, volume, temperature, mass of the gas. We're going to look a bit at the constants as well, what's given to you in exams. The concept of absolute zero temperature, the idea of Kelvin. Kelvin is a temperature scale. The ideal gas equations, we've got two that come up, which is the molecular one, the molar one rather, and the molecular one. So your R and your K are the two different constants which determine that. We've done a little bit about work done equals P delta V. In other words, change of volume and pressure equals the amount of energy done or is done by a gas or onto a gas. And then we'll, like I said, we'll look at those constants. There's a required practical that's associated with this part of it. I'm not going to do that in this lesson. I'll do that in a different one. It's a bit too much for one lesson. Okay, let's crack on. So before we do any new learning, we've got to make sure that our brains are warmed up. So these topics on here are around nuclear physics. They're around astrophysics as well. There's a little bit on thermal physics as well. So go in there, pick 3 or 4 of those, get warmed up, get your brain going. It's like exercise. You can't just go straight in on a cold brain. So just get your mind back into physics and astrophysics. And there's a few on there that you can't do yet, but you will by the end of this lesson. Okay. Right, once you've done that, come back to me. Okay, here we go. Get your notes out. Gas laws, absolute zero, Avogadro, and PV equals nRT. There's other gas equations, but PV equals nRT is the one that I think will tell you everything about a gas. It'll tell you how it behaves and what it's going to do. I've split all these up into the different proportionality laws. So, for instance, Ball's, Charles, pressure and amount laws. Boyle, wrote Boyle and Charles, the two chaps that did the initial experiments on these experiments, and then which you need to know the required practical for. And then I'll go through a bit about putting those all together into a single equation. The ones at the bottom. We're going to look at moles again. I know nobody really likes doing moles, but hopefully I'll be able to teach you how to deal with them. And just behind my head it just says Boltzmann constant, and that's the equation for Boltzmann and the molar gas law as well. So once you've got those written down in your notes, because you need to you need to write them down to make sure you try and remember those, then you're in good position to get going. So once you've got those written down, just pause the video and then we'll start again. Okay, so we've got 4 gas laws that we can derive from this single beautiful equation. Now, at some point, I'm going to derive a relationship from for PV using just a ball flying around in a box. At the moment, I'm going to leave that for the minute, and you're going to take this on board as the equation that relates pressure, lowercase p, volume, uppercase V, N, which is the number of moles, and R, which is the molar gas constant, 8 and a bit. It's on the formula sheet. Go and look for it. And T, which is temperature measured in Kelvin. Pressure is in pascals. Volume is in meters cubed. Be careful, chemists. This is meters cubed here. N, of course, is a whole number because it's just number of moles. R has its own unit. And T is in Kelvin. It's got to be like that, otherwise this equation does not work. Okay, you've got to be crystal clear on that one. So we can break this down. We can look at different parts. So we can make some things constant, and we can make, to be able to use this equation, we've got to make some certain assumptions about ideal gases. And the word ideal gases means that we're going to take some reality out of it, like the idea that the particles have size, the fact that they might hit each other and lose some energy, that kind of thing. And there's a finite number of them. So we get rid of all that troublesome stuff, and we end up with a model that works for that equation that I just showed you, PV equals nRT. Now, the first idea is that particles were running around randomly and in a random direction and moving very quickly as well, which we'll find out later on. Comes from some observations by a chap called Mr. Brown. And he looked at pollen grains in water and saw the pollen grains being bashed around, but they weren't hitting each other. They were just being bashed around by something, and they couldn't see anything. And he postulated that it was the idea that it was the water molecules that were actually hitting it and making it going in random directions. And then when we look at particles, smoke particles, they also are moving in random directions, not hitting each other. They're actually hitting the air molecules, which are hitting them extremely quickly. So he postulated that the air molecules must be going very quickly to be able to influence something as large as a smoke particle, and also in random directions. And that's part of the building up of this model. And so I've got 6 here. This is not exhaustive. There is more than this, but this is enough for A level. Basically, there are a large number of particles. It's a statistical law, one of the first statistical laws that was formulated, and then, of course, statistical laws are now govern quantum mechanics. Go and read up about Bose-Einstein statistics if you like. Also, they're perfectly elastic. That means that they don't lose any energy, no kinetic energy at all. Length of time between collisions is significantly longer than the time of collisions. So it means that we've got everything is just moving. There's no idea of the squashiness of something and then going, this is just a bit like billiard balls. The volume of the particles is negligible compared to the container, so in other words, they don't appear to have any size. They're random motions. There's no resultant force on them as well. That's kind of together. So in other words, we discount gravity or electrostatic forces or anything like that. And importantly, there are no intermolecular forces at all. So no external forces and no intermolecular forces either. So that's a good idea. In other words, you're stripping away reality and you've just got balls in a box that are banging into each other. And Bernoulli, of course, was one of the first people that came up with this idea back in 1738, and the idea of balls going around. Now, the size of the arrows, of course, here relate to the speeds, and there is a seemingly random distribution of speeds. Now, we're going to put some flesh on that bones later on about, depending on the temperature, you have an idea of the different ranges of speeds. This A-level course doesn't really deal with the idea of this distribution of speeds, but we'll look at it. If you did the astrophysics course, you will see the black bottom distribution, very similar distribution of energies in particles, in gases as well. And you can go and look at the Maxwell-Boltzmann distribution if you want to look in some detail at it. But just to put this here, is basically the idea is that we have balls in a box that are going in random directions. They're not affected by each other or anything else, and they're hitting the sides and they're not losing any energy. Simple as that. Okay, so when we look at the different gas laws, we can sort of split it up. So PV equals nRT. Behind my head it says sketch P versus V. In other words, what is the relationship between pressure and volume? Now, Boyle's law says that pressure times volume is a constant, so therefore pressure is proportional to 1 over V. I couldn't find a proportionality sign on PowerPoint. If anybody wants to put a comment in the video below and tell me how to do that, that's great. That's an infinity sign. That should be proportional. Anyway, the pressure increases with decreasing volume. So, in other words, if that shrinks and shrinks, your pressure will increase. Makes sense. The particles are hitting the sides of the vessel more frequently, so therefore you're going to get more pressure. In other words, more strikes of the balls hitting the side, so therefore there will be greater force felt on the side of that box. And what does P versus V look like? It looks a bit like that. You've got an inverse relationship law. Now you've got 2 lines drawn on here, one of T1 and one of T2. T2 is the higher temperature and T1 is the lower temperature. It makes sense, really, if you think about it. You've got greater pressures cause the greater volume. So therefore, it's intuitive in my mind. You have to think about these things in terms of balls in a box, and it all comes. Right. Next one is Charles' law, which is V over T equals constant, or V is proportional to T. So if the volume increases, the temperature of the gas increases, which makes sense. If I increase the temperature, the volume increases. Yes, that makes sense completely. So in other words, if I have the temperature, the balls start rattling around even more, they force this imaginary balloon I've got here to increase. So increase the temperature, the volume will increase if the pressure is kept the same. So that means I'm allowing that to increase in volume in order to keep that pressure the same. Makes sense. So V of t, whoa, I forgot I did that one. Right, so V against T will give you a proportionality, your pressure 1 and pressure P1 and P2. Which is the higher pressure one? Yes, P1 is the higher pressure one because you've got greater temperatures with smaller volumes. So therefore you've got greater temperature, therefore the particles are moving quickly. If you've got a high temperature, the speed is directly proportional to that. Remember that from AS and remember that from GCSE. Higher the temperature, the faster the particles. Actually, I'm on QTS3 and QTS2 as well. Therefore your volume makes sense. Say it out loud. A higher temperature, if you've got a small volume, of course the pressure is going to be higher because it's smacking into the side even more. Worth saying out loud. And there it goes again. Duck as it comes through. Right, we've got pressure law here. P divided by T is constant. So you've got pressure proportional to temperature. In this case, again, makes sense. If the temperature increases, the pressure will increase at constant volume. So if I keep that concrete balloon I've said here, constant volume, if I increase the temperature, that pressure is going to get greater and greater. It's very, it makes sense. Again, it's like a pressure cooker. Keep the volume the same, increase the temperature, the pressure is going to increase. So therefore, I'm going to just got a shaking balloon there. P versus T. There you go. We've got temperature on the bottom, pressure at the side. Here, it's proportional. We've got those dot dots. I'll come back to why those dot dots are there soon. And you've got two different volumes now. Which is the higher? Which is the greater volume, I should say. I'm going to say higher temperature then. Which is the greater volume? So I've got higher temperatures at low pressure. If I've got pressure, I've got temperatures and high volume. V1. Okay. Right, so we've got Avogadro's. I've called it the constant law here. And it's Avogadro's. Basically, it's the amount law. You've got stuff going in. Basically, if you put more particles into it, your pressure will increase with a constant volume and temperature. This makes sense again. I always imagine it being a bit like the bicycle blowing up law, which is basically your volume of your tyre stays roughly the same. If you put more stuff in, the pressure increases. Nothing too earth-shattering about that. So pressure proportional to that's going to be just proportional to. So as a practice, we've got this exam question here. The graph shows that the pressure of initial gas varies with volume with its mass and temperature of the gas constant. So it's very similar to what we saw at the start. On the axis, get two different curves. A and B of the following changes are made. The same mass of gas at a lower constant temperature, a greater mass of gas at the original constant temperature. So have a think about this. Same mass of gas at lower temperature. So if you've got lower temperature, is the pressure going to be lower and the volume going to be lower? Is the pressure going to be greater and the volume going to be greater in any particular part? I think it'd be pretty obvious really. Lower temperature, lower pressure. So you end up with a curve that just rolls just beneath here. Okay. Now, greater mass of gas, original temperature. So now I'm stuffing more particles in. Does that mean the pressure is going to increase on this particular particle? Of course it does, because I've got more particles in. They're hitting the side more frequently. So therefore my pressure is going to increase. And therefore my volume is also going to increase as well. So therefore you've got this idea that this line is actually scooting above this one here as well. So cylinder of volume that much contains ideal gas pressure that much. Kilopascals, that's how it looks like, kilopascals. Temperature of 290 Kelvin, no need for any conversion there, it's been given in Kelvin. And the amount of gas in moles in the cylinder. So get your calculator out, PV equals nRT. R, by the way, is 8.31. You should have your formula sheet in front of you all the time for these ones. And you should be able to calculate the gas. And here we are, just the answers. Curve A is below the original, curve B is above the original. Both curves have the same shape, of course. And there you go, there's the calculation. There's your kilopascals, because it's got the 10 to the 3. There's your molar gas constant, there's your kilo, and you end up with 11 moles. A nice, easy number. Notice it's actually 10.8, but because you've been given two significant figures for here and here, that means that is two significant figures should be given. Concentrate. that occurs through A-level physics. One of the most important parts of this unit is the ability to be able to compare gases before a situation and to after. In other words, I'm going to change some variable. I call these the ratio laws. And the reason is that most calculations can be done in a far easier way by just equating something to a constant. Now, all I've done here is taken PV equals nRT and assume that n is the same and r is the same. R is always the same because it's a universal constant. N is the amount of gas. As long as the amount of gas stays the same, then you're safe to be able to use this. In other words, PV over T beforehand will equal PV over T afterwards because I've got the same amount of gas. So therefore, whatever I do to any of these, the other variables will adjust. I can do it with all three. I can do it with just two of them, assuming pressure and moles are the same. I can do it with P and T, assuming that volume and the moles are the same. I can do it with P and V, assuming that temperature and the moles are the same. So when you're dealing with problems where a gas does this and then a gas is doing this, so for instance, you start off with this situation, for instance, let's take the last one, your pressure is atmospheric pressure, say, and the volume is 1 square meter. And then the volume of that is squashed. So for instance, I go to half a cubic meter rather. Sorry, cubic meter should have said, half a cubic meter. Therefore, what's your new pressure? And all you have to do is stick the numbers in and work out what the other pressure is. Really important to have this, especially with the multiple choice questions with A-level. They love this sort of thing, and it's a real quick and easy way to be able to compare the situation of the gas beforehand to the situation of the gas afterwards. And this is an example of what we were doing. So in other words, we've got to have in our back pocket all of the time PV equals nRT and think of all those ratio ones as well. Now, if you're thinking, I didn't even see those ratio ones, I haven't written them down. You can get them all from here. Basically, from PV equals nRT, all I have to do is basically put the variables that I've been given on one side and put all the constants on the other, and then you have how it looks. So for instance, if I just have been given pressure and volume, it's PV equals PV because if temperature is the same, all these others are the same. If it's pressure and temperature, for instance, I just bring T down here, take V over here, and it's P over T equals P over T, before and after. So let's have a look at this example. 5 mole, so that just means 5 moles. A sample of nitrogen exerts pressure of 150 kilopascals at a temperature of 373 Kelvin. What is the volume of the sample? That's just P equals nRT. Just do the calculation. The temperature has changed to 273 and the pressure drops to this. What is the volume now? Now this is a classic example of using PV over T equals PV over T. Why can we do that? Because N and R are the same. And we'll be asked to work out what the mystery volume is. So get your calculator out, go away, put those, don't go away, carry on, and put those numbers in. You know the pressure, you know the temperature, and you're just working out the volume for the second part. Of course, you know all three for the first situation, so put all three on the left-hand side and put all the other on the other side, and you will be able to calculate a new volume. Answers coming. And here they are. So you've got P equals nRT, so 0.1 cubic meter, and then the next one, of course, is that the temperature changed to 273 and the pressure drops. Therefore, you've got a slightly larger volume of 0.0. Right, next one. Sample of gas at pressure this. 100 pascals is a volume of 5 litres. Litres? What's going on? I thought it was in meters cubed. But wait, this is why it's useful. And a temperature of 7C. See what they're doing there? The pressure now drops to 80,000 pascals and the temperature increases by 40 C. It increases by 40 C. Remember, Celsius and Kelvin are the same size. Calculate the new volume. Okay, so let's have a look at this one. We've got lots of different bits and pieces, but we can still use the ratio law here. Now, because it's a ratio, we don't care what the units are as long as they're the same before and afterwards. So in this case, we can get an answer in litres for our new volume. So PV over T, and PV over T equals PV over T. You've got your pressure, 1,000. You've got your V. You've got your 5 litres, so it's 5. In this case, you need to convert this into Kelvin. Now, if you haven't done this yet, of course, Kelvin is 273. Kelvin is 0 degrees centigrade. So if it's 7, it's just 7 above 273. So that's 280 Kelvin. And then, of course, we've got the temperature increases by 40. So I've got my 280, therefore that has to be 320. And therefore, I've got all my numbers to be able to do it. So do your before, do your afterwards. And then number 4 is an excellent estimation one. I love these ones. And these do occur in exams, by the way, because you have to know rough figures. So atmospheric pressure is about 100,000 pascals and the temperature is about 300 Kelvin. Estimate the number of the moles of air in the room you're in now. Now, you might be in a big room, you're in a small room, so get your meters cubed. So meters, wide, depth, height, get your volume, and there you go. You've got your temperature and your pressure, and therefore you can get the total number of moles in that room. Answers coming. 3, 2, 1. And there we are. So we end up with about 7 litres, which is 7.4, 14 down there. Anyway, the V on the top one's right, 6.99 litres. And then I've used the roughly a lab, so 3 times 10 times 10, give or take. So you end up with a mass of about 360 kilograms of that, but it really depends on what the size of your room is. So you end up with many moles, basically, a lot of moles. But I always think it's incredible. It's about a quarter of a ton of air in a lab. Nobody thinks of it as the air is weighing something, but there it is. Okay, next. Molar mass of carbon dioxide is 0.045 kilograms per mole. So depending on how many moles I have, I can work out the mass of something. Calculate the density of the gas when the temperature is 273 and the pressure is 1200 pascals. Now, very common one, this one, mixing up various parts of the course. So we know density is mass divided by volume. Mass divided by volume, that's where the volume comes from, you see. So therefore, you're going to need to be able to rearrange PV equals nRT to get N over V. Now, the N, of course, is number of moles. And we've got a number of kilograms per mole. That's great. So all I have to do is just basically put 0.05 in, because that's how many kilograms per mole I've got. And just stick that number in, and then we can get the density of the gas in there. And of course, you've got the temperature in Kelvin, you've got the pressure in pascals. No problem. I'll show you the answers in a second. There's some clues for you to give it a work out. Then, of course, the next question here, the summit of Mount Everest can be a temperature of minus 50 degrees C. Pressure at summit is roughly 1/3 that at sea level. And the density of air in your laboratory is about 1.25 kilograms per meter cubed. Calculate the density of air at the top of the mountain. Now, this is a ratio question. It's also a trick question in that you have Celsius in Kelvin. So this one here should need to be converted into Kelvin. Do that. We've got the density again. We've got kilograms per meter cubed in here to be able to work that out. And then to be able to, we haven't got a moles one, so it's like, oh, what's going on here? We've got kilograms all of a sudden. So we need to do something with that, basically, to be able to get it. Now think, remember, at all times, you're going to try and work out density, which is mass divided by volume. And this here is already giving you that mass divided by volume. The only difficult thing is converting moles into mass. That's the only difficult thing. So have a think about that, give it a try, and I can give the answers in a second. Okay, here we go. And this was hard. So you can see by the amount of working I've got on here. So the top one, density is mass divided by volume. Molar mass is mass divided by moles. Not given on the formula sheet. You'll be asked to just remember that one. Therefore, mass is molar mass times moles. So density is molar mass times moles divided by volume. And you can see here moles over volume is actually in the PV equals nRT. So P equals nRT, we just rearrange to get V equals nRT over P. So density, molar mass times moles here, divided by this number here, of course, because I've got the volume, because I'm trying to get the volume on here. Density, this is what I'm working out here, is pressure times molar mass times moles, divided by moles times R times T. Now, I'll say that again slowly. You're getting an expression for volume. You want the density, so therefore you're going to substitute your equation for volume into this equation that we've got here, which is mass divided by volume. There's your mass from the top here, and there's your volume from this one here. So you might think, oh God, what a mess, but this is how you do it. Actually, you shake it down and you end up with density is P times molar mass divided by RT. You can see things have cancelled out, things have stayed there, number of moles, N gets cancelled out here, of course, and pressure just pops up to the top, and so you end up with an expression for those three. Density is pressure, 120,000 times molar mass, got that one, gas, molar gas constant and temperature gives you that 2.38 meters cubed. Why is it three significant figures? Because there are three significant figures up here. So again, here we go. We've got a new problem here. We've got to convert this to Kelvin. Let's have a look. So it's ratio required. We've got PV equals nRT, PV equals nRV. Again, it's that density one, substitute density, and we end up with the same equation we had before. So in other words, in this case, we've got pressure in lab times molar mass over this is equal to pressure at summit, molar mass times density at the summit as well. So therefore, we stick all these numbers in here. So 1 over this, so 1 divided by here. And then we've got the unknowns here, which is density at the summit, 0.3, which is 1/3 that at sea level. This 1 and this 0.3 here come from the fact that the pressure is dropped to 1/3 of what it was before. So we don't actually need to know the numbers. This is what's nice about the ratio. 1. These are the temperatures, of course. That's at the lab, that's at the summit. And then, of course, we want to know what this difference in density is here. And we end up with this value here. Now, I don't expect you to be able to understand that first time around. So pause this, look at the video, work out where those come from as well. Okay. The only thing that's behind here, by the way, is just T times density in summit. And you can see the other. It's difficult trying to put where my head is. And you've got to practice these. I've got to recommend going to Physics and Maths Tutor website because they've got hundreds of questions on these. You've got to practice. PV equals nRT and ratio laws are just about practicing over and over again. And I've been asked by some students to just do practice questions from the exams, which I can do as well, and I'll get around to doing those soon. I've just popped up at the top here. There's another equation which you can be useful if you have Avogadro's constant, which is Na, which is given on your formula sheet. And this N is still number of moles. The only difference is you've got to use Boltzmann's constant. I'll come back to where that is and how that uses as well. I think this is Lord Kelvin. I think that's Lord Kelvin telling you to practice while you sleep. Basically, the people who do well in exams practice more than everybody else. Not listening to YouTube videos, I'm afraid. This is a good how to start, but you get a good grade by what happens when you pause this video and what you do afterwards. So keep working hard. Just to recap here, we've done this one. We haven't done the concept of absolute zero as yet. I'll do that in the next lesson. Ideal gas equation. Go back and look at the assumptions for an ideal gas. Haven't touched this yet, but I'll come back to this yet. And we've looked at Avogadro's constant, molar gas constant, Boltzmann constant. They all come in. Avogadro's constant, of course, is just 6.123 times 10 to the power 23 particles in a mole. You should have done that in chemistry. You should have done that at GCSE. Molar gas constant, as you've seen, Boltzmann constant, is just a replacement of that within that equation. And then I'll do this another one. Okay, well, thanks for listening. That was a long one. It's hard, this stuff. You need to practice it.